So let's keep going. Set up the integral needed to find the volume of the solid whose base is the area bounded by the following. So I have a circle. It's going to be similar to that picture that you saw over here. The base is a circle. And it says, and whose cross sections are equilateral triangles, perpendicular to the x-axis. So if I were to draw equilateral triangles, it looks like this. So the base is a circle, and the cross sections are equilateral triangles. Okay, so let me go ahead and do that right there. Okay, where I have the x-axis kind of going through here. I have the y-axis going up here. This is kind of going through, if you will. I'll just go through it. And then the base is a circle. So if I were to look at the base and kind of give it a three-dimensional rendering, it goes through the shape. It looks something like that. Okay. So what we're trying to do now is we're trying to figure out what would the volume be if all these are equilateral triangles. So like, let's go to not the first, second, but third one. There's the base, it goes up, it's like that. This is one cross-sectional equilateral triangle. Okay, and how many are there in between the very, very far left and the very, very far right? There's infinite number of them. Okay, that's why we're integrating these from A to B. Okay, so let's go back. Let's go ahead and come up with the equation here as far as the area of an equilateral triangle. This should be memorized. If you don't have it memorized, you can always on the fly say to yourself, well, I know an equilateral triangle, there's 60, 60, and 60. I can create a 30, 60, 90. So 30, 60, 90 right triangle. Give the hypotenuse 2x, 2x, and 2x. So that if I was just looking at this, I know this is x, this is 2x, this would be x root 3. Okay? And the equation for the, again, this is a 30, 60, 90 triangle. You can record or rewind this video or pause it, whatever, if you need to look at how this works. So it's base times height, so base times the height, which is x root 3, divided by 2. So base times height divided by 2. That's how you get this side squared business as far as what it's going to equal, like an area of the equilateral triangle. Okay, so let me look at something real quick. So base times height divided by 2. Where is this? Trying to figure out where the 4 comes into play. The base, what did I do? 1/2 times base times height. Yeah, so base times height divided by 2, just like I said. Base times height divided by 2 would be 2x times x root 3 divided by 2. The 2's would cancel, and you'd be with x squared, and then that root 3. Okay, so the reason why there's that 1/4 is the fact that here it's side squared. Okay, so side squared, I'm going to say s is equal to 2x, so that x is equal to side divided by 2. So that whenever I'm looking at this, I could put in, where I see an s, I would put 2x. Okay? So again, each of the length of these sides, like I highlighted here in green, is going to be 2x. So 2x is equal to s. If I put 2x here for s, you would see 2x squared root 3, and it would be over 4. Okay? Now I know this is a little bit confusing, but it's basically going to show that my x value is, my s value is 2x. So it'd be, okay, so putting into the equation 2x squared root 3 over 4 would equal, okay, so 4 squared, or 2 squared is 4, x squared is x squared. So you would get that cancellation. So it's still going to be that x squared root 3 is equal to the x squared root 3 that we got. So instead of just working with all that and trying to figure out on the fly what is the area formula from an equilateral triangle, you're just going to go ahead and memorize that. So the area formula would be s squared is root 3, or s squared times root 3 over 4. Okay, so perpendicular to the x-axis. Okay, so if you need to draw that just real quick, here's the x. Perpendicular, they're going to be dx's. They're vertical slices. Okay, and they're all equilateral triangle. We already saw that from the picture over here, what that would look like. Okay, so I need to integrate the area in respect, or in terms of x, in respect to x, because they're vertical slices, and we're going to go from the bottom, or from the low to the high. Okay, so again, this is a circle, so let's draw the base. Well, you should know by now that this circle right here has a 0, 0 center to it with a radius of 3. So 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. It looks something like this as far as the base is concerned. Okay? And if I were to draw the base of one of these equilateral triangle, it's like this could be a base here. Okay, and it would pop up out of your picture that looks something like this. And a better orientation as far as the way it would look like on a three-dimensional rendering, which is what I keep going back to. Here's your y, here's your x, and then straight up is your z. And then looking at it like a three-dimensional rendering, here's your circle. And let me highlight in purple the base of this equilateral triangle, because it doesn't really look like an equilateral triangle when you look at it from the area view, but whenever you do it here, it pops up out of the page, and you can see that equilateral triangle a little bit more. Okay, and again, if you need to go back to the Wolfram demonstrations and kind of try to visualize what these equilateral triangles are, you can. Okay, like the very end, it'd be a small little equilateral triangle because you're just looking at it from that base's small point of view. It depends on what is the distance between the top and the bottom. That'll dictate how big the equilateral triangle pops out of the page from. Okay? So, the low to the high will be -3 to 3. Now, the equilateral triangle, the area formula is going to go right here where a of x is at. So, it's like -3 to 3. And I might have said that wrong earlier. I might have said -√3 or +√3. The bounds are -3 to 3, and it's going to be s squared √3 over 4. I'm going to take this √3 over 4 out, constant multiple rule, and I'm going to take it out and put it in front of the actual integrand. So √3 over 4, and then it's going to be dx. The only thing that I need to do now is I need to write s, which is that variable in my equation. I need to write it in terms of x, because I have in respect to x right there written. So I need to write s in terms of x. And again, the s is the length of the side. So I could say this length right here is s. This length right here is s. This length right here. And from the perspective, as far as from an aerial point of view, it's that base right there. Now, the fact that I have the circle with the radius of 3, this length, well, like if I said right here, what would the length of this diameter be? Well, you know it'd be 6, because you have 3 here and you have 3 here. But it's not going to be 6, obviously, throughout this entire interval. It's going to get smaller as you go to the right, and it's going to get smaller as you go to the left. So we need to figure out, find this, and solve it in terms of x, so that you can write, or so that you can integrate this in respect to x integral. Okay? So I need to write s in terms of x. So what does that mean? I need to get y by itself. So y squared is equal to 9 minus x squared. And then y is equal to plus or minus the square root of 9 minus x squared. And looking at that, if I said the plus or minus square root, the plus will go here. The minus will go here. So when I'm looking at this, I could just say, I'm just going to take half of it, which means y is equal to this square root of 9 minus x squared, and that can be the positive half. That can be the top one. Let me highlight that in orange so that you see what I'm talking about. Right here is what I'm looking at. That positive 9 minus x squared. Okay, so there's that positive square root of 9 minus x squared. Okay, when I put that over here for s, that's going to be half of one side. Okay, that's going to be half of one side because the entire side is if I were to do the entire base. And let me highlight that now in green. I have a lot of highlights going on. So this entire thing would be the entire S. Okay, the entire side length of the equilateral triangle. So what is it that I'm going to do? I'm going to end up multiplying this half diameter, or this radius if you will. I'm going to multiply it by 2 because that will give me the entire side. So 2 times 9 minus x squared. This right here is the length of any given side as you go throughout this entire interval. So as you go from left to right, and you have the big one, you have the bigger one, and you have the very small one, and again you have the very small one on the very far left as well, this will account for the changes that length will take, that length of that S will take. Okay? And it's all going to be squared. Okay? So it's going to be that S value squared, and it's going to be from negative 3 to 3. Square root of 3 and dx. And some of you are probably recognizing, ooh, I have a 2 squared. So could I constant multiple roll out of 4? Yeah, you can. So if you wrote that 4 out and you constant multiple rolled it out, it would cancel with this denominator, where you'd have root 3 from negative 3 to 3, and it'll be the square root of 9 minus x squared. So if I square the square root, I'm just going to get 9 minus x squared. So either one of these would work. Okay? To start off, I would suggest doing this one down here. Okay, let me go ahead and box that. But if you understand and you can cancel and manipulate and stuff, you can see that that is equivalent the same. Okay, so let me go ahead and now find this area. Okay, so we have pi over 4. I'm going to go ahead and do the first one. It's going to be multiplied by the integral from negative 3 to 3. And it's going to be the 2, okay, so here we go. 2 times the square root of 9 minus x squared, and its quantity will be squared because it was s squared, and it's going to be in respect to x, and you get, whoops, and you get 113.097. Again, if I put the square root of 3, this other alternative form that we did over here, I should get the same answer. Okay, so let me go ahead and do that real quick. So the square root of 3 times the integral, the definite integral, and, whoops, I put that underneath the thing. So let me kick out. Then multiply by, take that off too. Multiply by the definite integral, and it'll be from negative 3 to 3. And then, again, because I squared that square root, it canceled, and I get 9 minus x squared. So I get 9 minus x squared. And some of you, a lot of you will do this differently, but you should still get the same answer of 113 point. Uh-oh, something happened. So 9 minus x squared, let's see what we did. 9 minus x squared dx, and obviously it's half off. So 2 squared is 4, 4. Oh, that's why. Because I shouldn't have put pi on the first one. I should have put root 3. So I discovered my mistake before I got the emails. This right here, I should have, instead of putting pi, I should have put root 3. I don't know why I put pi. Okay, so let me come over here, and let me make this a root 3. So now they should be equivalent. They should be 62.354. 62.354, yeah, that's what I got. So 62.354 units cubed, because it's volume. And if you wanted to truncate, you could just put 353, okay, instead of rounding it. Either one of those are the only ones that will be allowed. Again, you cannot be more than 1/1000th of a point off, okay? So let's now go to the base of a solid is bounded by the following. So we have x squared we have y is equal to 0, otherwise the x-axis. Then we have x is equal to 2. And then for this solid, each cross-section perpendicular to the, let me go ahead and do that in black, perpendicular to the y-axis. So if you're perpendicular to the y-axis, you know that's the y-axis here. Here's the x. Perpendicular to the y-axis is a 90 degree. That's horizontal, so that's dy's. So horizontal, it's going to look like this. These are the slices. And you know that it's going to be dy. Set up the integral needed to find the volume of this solid. Okay, so what are these? These are the bases. All these lines that I did that were horizontal are bases of a square. So if I were to draw one of them, it would look like this. And then as I go through the function, okay, like here's a big square. And then there at the very end will be a small little square because the base is really, really small. Okay, and you should see by now what these are looking like. So the bigger one at the very, very front, and then they get smaller and smaller and smaller all the way back until they go infinitely approaching the width of 0. Okay, so you know this is dy. So they're going to be horizontal slices. And horizontal slices, we got to tilt our head to the right so that we're going to tilt our head to the right 90 degrees so that we can see what's the top function and what's the bottom function. So the top function you should see is going to be the purple and the bottom is going to be the red. And then you're going to go from low, which is the x-axis, all the way to high, which is whatever that intersection is here. Okay, because we're trying to find this area right there. Okay, so let me undo that real quick. And let's go ahead and start setting it up. We know it's going to be a of y. It's going to be dy. And if I looked at the intersections of these two, I would intersect the x squared function with the x is equal to 2 function. Okay, so x is equal to 2 function, you're basically going to know that when is that going to exist? When does x is equal to 2 equal this x squared function? Okay, so looking at that, you're going to say x is equal to the square root of 2. Okay, that's what will be the y, the x value, or sorry, the place where these two will intersect. So setting x squared equal to 2. Hold on just a bit. What am I doing? Oh, will be 4. What am I doing? It'll be 4 as far as the y value. Okay? So x squared, think of it like this. x squared. When x is equal to 2 here, the output would be 4. Because this point right here is 2, 4. Okay? So from all the way y is equal to 0, all the way to, we did an example when we were doing the area ones, last day of notes. So from 0 to 4 is going to be the low to high. Okay, because you're looking at the y values because of the fact that you're in respect to y. Okay, so again, squares. So when you see a square, you know the area for a square is going to be side squared. So I need to come up with something that represents the side length. Okay, so the side length is going to be the top minus the bottom. This is where I would turn my head 90 degrees to the right. The top is 2 minus the bottom, which is, again, x squared. But we're not going to put x squared there. We can't put x squared there because we have to write it in terms of y. So let's solve this guy right here for x. We get y, or the positive and negative square root of y is equal to x. So now that we did it, we should know by now that this piece of the graph, let me highlight it real quick in green. This piece of the graph is going to be the positive square root of y. Okay, so the positive square root of y, that's what's going to go right there. Okay, and let me go ahead and write that in right now. So the top function in terms of y is going to be 2. Okay, minus the bottom function in terms of y is going to be the square root of y. And it's the positive one. And we're going to do a dy right here. So top is 2 minus the square root of y is the bottom one. and it's going to be from 0 to 4. Okay, so from there, you can put it into your calculator. You can do this by hand. Just for the sake of practice, we're going to do it by hand and then check with the calculator real quick. But just want to make sure that I have everything set up according to what I need to. So side is side squared. Side squared, we said that comes from the top minus the bottom. The top minus the bottom had to be interpreted dy because it's horizontal slices. And the top was 2 minus the square root of y. And again, that's the most important piece right here, is the square root of y comes from solving for x, because we get it written in terms of y. And then it'll be from 0 to 4. Again, 0 to 4, you don't have to tilt your head to find 0 to 4. You look at it from low to high, and that's what you're integrating as far as that interval right there. Alright, so we'll get 2y minus, and just real quick so that you see this, this is y to the 1/2. And y to the 1/2, it's reverse power rule, so you're going to add 1. So it'll be y to the 3/2, and then 2/3. So this is going to be from 0 to 4. This is what this is equal to. So we'd say 8 minus, now here we go. It's been a while. When I plug this 4 in here, I'm not going to cube it first. I'm going to square root it. So the square root of 4 is 2. Then cube that to get 8. Multiply by 2 to get 16, and I get 16/3. Minus, plug in the 0. When I plug in the 0, I get zeros here for this particular one. You won't always get zeros, so don't go into autopilot with that, but for this one, we did. Common denominator is 3, so we get 24 over 3 minus 16 over 3. So you get 8 over 3, 8/3, or 2.666, or 2.667. We'll say 2.667. And let's see if we get that when we plug this into our calculator. So here we go real quick. So the definite integral from 0 to 4, and it's going to be, let me come over here, from 2 minus the square root of y. So we go 2 minus the square root of y. Whoops, that's not what I want. The square root of y, and it is dy. And we should get the 8/3, okay? And that 8/3 is what we got from before, or 2.667. Again, if I go up there and I press Control Enter, I get 2.667. Control Enter, get 2.667. Okay, and don't pay any attention to this. I'm glad I did it like that. Don't pay any attention to this exclamation point warning sign. It doesn't necessarily mean that you got it wrong. It just means it means different things that you're not yet exposed to. You'll get exposed to like in college or whatnot, if and only if y'all use this certain calculator in y'all's class. But don't think that that's a mistake, okay? Obviously it's still correct. It's just giving you warnings of other things. Now, if I come over here and I said, I know that I took horizontal slices. Because I know I took horizontal slices, I chose to use y. But again, that's just so that I can find out what are the equations going to be written whenever I need to do them in terms of something. But if I come over here and I change this to x, first of all, it's not going to compute and give me a solid number because it's doing multivariable calculus. That's Calc 3 in college. You're not doing that right now. You got to get it the same variable. So I'll come over here and I'll change this y to x. And would I get 8/3? Well, yes, I would. I'd get 8/3 because of the fact that it's technically the same integral. This right here is the same integral as this one up here. The only difference is that you've chosen to use a different variable. But it's still the same integral as far as finding the calculated quantity of 8/3. Okay, so 8/3, we'll put equals 8/3. Technically, that's more accurate than 2.667 cubed, but I'll take the 2.667 if you did that as well. And yes, all these other ones are units cubed as well.